Hey everyone, in the last video we talked about tables and LSM trees and how they overcome the limitations of append-only log with a hash index. And this video is about B trees and how they are used as an indexing structure in databases. Now the log structured indexes that we have discussed in the previous video, they are gaining acceptance, but they are not the most common type of index. So the most common type of, the most widely used indexing structure is actually called the B tree. So the B tree is the standard index implementation in almost all the relational databases that we have right now. Now the log structured indexes that we saw earlier, it usually breaks down the database into variable size segments, and those segments are typically several megabytes or more in size. By contrast, a B tree, it breaks the database down into fixed size blocks or pages, and those pages are traditionally 4 kilobytes in size, or they are sometimes even bigger. Now this design corresponds more closely to the underlying hardware because disks, they are also arranged in fixed size blocks. Also, each page in the B tree, it's identified using an address, and the pages, they refer to one another using pointers. Now since these pages exist on disk, so the reference that we are talking about, that also exists on the disk and not on memory. Now we use those page references to construct a tree of pages. So that's why this structure is called a tree. Now this is the way how a lookup in a B tree works, and let's understand this with an example. So let's say we have a B tree here which stores the user IDs for a database, and we want to look up the user ID 251 here. So in a B tree, one page is designated as the root of the B tree. So whenever you want to look up a key in the index, you start from the root. So in this example here, this page at the top, this is the root of this B tree. Now every page, it contains several keys and references to the child pages. So in this root page, we have all the references which are pointing to the child pages. And this root page is responsible for these set of keys from 100, 200, 300, 400, and then 500. Now since in this case we are looking for the key 251 here, so we know that we need to follow the page reference between the boundaries 200 and 300 here. So in this case we have a reference between the key 200 and 300, and this reference is pointing to one of the child pages here. Now this takes us to a similar looking page, and this page, it further breaks down the range between 200 to 300 into further sub ranges. So eventually we get down to a page which contains individual keys, and this page down at the top, it's called a leaf page. So in this case we can see that it has this value, it has this key 251, and this val here, it means the value which corresponds to these keys. So this is the way by which we can track down the references from a root page into its child pages and then find a key in that index. Now similarly, if you want to add a new key in the B tree, you need to find a page whose range encompasses the new key and then add it to that page. So let's also understand this with an example. Now let's say you have this existing B tree and you want to add a new key 334 in this tree. So for this we have this page right at the top, and in this page it has the keys 310, 333 and 345. Now the key 334 will go in one of the child pages, and the reference for that we can find between these two keys 333 and 345. Now we come to a leaf page down here. So in this leaf page, the key 334, it will go in between these two keys 333 and 335. Now we don't want to make a B tree arbitrarily large, so this page here, this is split to accommodate the new key. So in this case it is split into two half full pages. Now after this split, this left page, it contains all the keys and values up to the key 335, and this right page has all the keys which are greater than 335. So in this case we can see that this the parent page that we have, that is also updated to account for the new subdivision of key ranges. So this is how we can add a new key by add a new key into the B tree by splitting the a page into subpages. Now this split and grow algorithm that we saw, it ensures that the tree always remains balanced. So a B tree that has n keys, it always has a depth of O of log n. So also most of our production databases that we have, they can easily fit into a B tree that is at max 3 or 4 levels deep. So in most of the use cases, you don't have to follow many page references and go very deep to find the page that you are looking for. Now DB crashes, it can lead to corrupted indexes, and this problem is more frequent in case of B trees. So this is because there are a lot of writes happening all the time on the disk in case of B trees. So as we saw in case of an insert or even an update, that when a B tree page becomes full, there are multiple writes happening in that case to both the parent and also the child pages on the disk. Now if the DB crashes, then these updates and when these updates are in progress, it will often lead to corrupted indexes. And this is in stark contrast to the log structure indexes such as LSM trees, because in those cases they only append to files but they never modify those files in place. So to make the database resilient to crashes, we use a write ahead log, and that's the standard implementation. So we have discussed this earlier also. It's an append only file to which every modification must be written before it can be applied to the pages of the tree itself. So okay, so when the database comes back up after a crash, this write ahead log is used to restore the backtree to a consistent state. Now since we have gone through both the B trees and LSM trees in detail, let's also see how they compare. Now in case of a B tree, as we discussed earlier, one write to a database, it results in multiple writes to the disk. So even in case of an update, you have to write the entire page at a time, even if let's say only a few bytes in that page has changed. So this increased number of writes on the disk, it's called write amplification. So B trees have very high write amplification naturally, and it's very concerning for the SSD hard drives because they can only overwrite blocks for a limited number of times before they actually start wearing out. So also LSM trees, they can be compressed better and they often have smaller files on the disk than the B trees. Because in case of B trees, they often leave some disk space unused due to the fragmentation issue. And this happens because when a page, let's say it's split, or when a row cannot fit into an existing page, some space in that B tree page, it always remains unused. So also since data is represented more compactly in LSM trees, it allows for more read and write requests within the available IO bandwidth. Now a downside of log structured storage is that the compaction process, it can sometimes interfere with the performance of ongoing reads and writes. So hard disks often have limited resources, so it can easily happen that a request, it needs to wait while the disk it is finishing an expensive compaction operation. Now the impact on throughput and average response time is it's usually small in this case, and maybe there won't be any difference to, let's say, the 99% of the queries, but it can still impact the remaining 1% of the queries. So also many relational databases, they implement transaction isolation using the locks on a range of keys. So in this approach, when let's say transaction accesses those range of keys, it acquires a lock on that range to prevent other concurrent transactions from modifying the same keys simultaneously. Now in a B tree index, the structure of the tree, it allows for attaching those locks directly to the tree nodes. So let's say when a transaction needs to access or modify a range of keys in the database, it can acquire the appropriate lock on the corresponding nodes in the B tree itself. So that's all we have for B tree and its pros and cons. Next we'll look into data warehousing and also column oriented storage.